All right, today, guys, we're going to look at 2.3 properties of functions. In class, I'm hopefully going to do a little activity with you guys where I identify some even and odd functions. We talked a little bit about that in Algebra 2, but we'll review it here again. So we have a lot of objectives for today. We're going to determine even and odd functions by looking at a picture of a graph. We're going to identify even and odd functions from an equation. We're going to use a graph to determine where a function is increasing, decreasing, or constant. We're going to use a graph to locate local maxima, local minima. We're going to use a graph to locate the absolute max, the absolute min. Then we're going to use a graphing utility to approximate locations of maximum and minimums. And we're going to find the average rate of change of a function. So a lot to do there. Probably going to break it up into two mini lessons. So let's get into it. Objective 1. We're going to determine an even and an odd function from a graph. Okay, so what you need to know and what you need to get into your notes and you need to make sure that you have a good understanding of is what an even and an odd function is. Basically, pictured here, we have an even function. Okay, by definition, an even function is basically saying if I plug in an x value, I get a y value out of a function, right? So if we have something like, let me just do this one here, y equals x squared. If I plug like a positive 2 into this, then y would equal 2 squared or 4, okay? The even function states that if you do this and plug in the negative x value, okay, so here we chose 2. Now what happens if I choose a negative 2, right? So if I have negative 2 squared, what the even function states is if you plug the negative of the x in, you will get out the same y result. Okay, so notice that's what they're trying to show you here. This point here has the same y value as this point over here. This y and this y are the same, okay? The only thing that's different is this is an x value we call x1, and over here is the negative of that x1. Okay, so it's just like what we were doing algebraically there. So that's even. Odd functions happen when you plug a negative x in. Okay, so if you have a standard x, you just plug in an x into a function, and then you plug the negative in. Do you get the same answer but with a negative result? Okay, so notice here that the y value just went to negative. Okay, so if you plug a negative x into the function, do you get a negative y out? So an example of that, a very easy example, probably the easiest example there is y equals x to the third power. Okay, so if I choose an x value of, let's just say 2, do the same one here, y equals 2 to the third, that is equal to 8, right? If I plug a negative x in, okay, so the negative 2 to the third, negative 2 to the third means negative 2 times negative 2 times negative 2. That would actually give me a negative 8. So notice I plug the negative x value in, I get the negative y value out. This will always have symmetry across the origin. Okay, so that's the odd function. So here's the theorem. If you still don't have it, here's the language of the theorem for even and odd functions. A function is even if and only if its graph is symmetric with respect to the y-axis. Okay, so those ones that I was talking to, y equals x squared, obviously, is this guy right here. It's symmetrical to the y-axis, right? So there's symmetry on either side of that line. And then a function is odd if and only if its graph is symmetric with respect to the origin. Okay, the origin would be this line right here. It could also be this line right here, right? So it doesn't matter if it's negative or positive. Okay, so example 1 says determine even and odd functions from the graph. Okay, so if I look at this picture, it appears to have symmetry across the y-axis. Therefore, this would be an even function. Okay, so you're just looking at the picture and determining, does it have symmetry? And is it across the y-axis or is it across the origin? Okay, so let's look at a couple more. If I look at B, okay, notice we do not have symmetry here, right? We don't have symmetry here. This point would have to be somewhere right here if there was symmetry across the y, right? If I looked at this line, I don't have symmetry across that line. If I look at this line, I don't have symmetry across that line either. Therefore, this is neither even or odd. Okay, if this guy would have been moved over a little bit, then it could have possibly been, if this shifted to the left, then it could have been an odd function, but it is not since there's no symmetry. But notice C. C is a little tricky, but not really. If you drew this dotted line through the origin here, notice we have a perfect reflection across that line. This is an example of an odd function. Okay, odd function. Objective 2 is identifying even and odd functions from an equation. All right, so from an equation, it says use a graphing utility to conjecture first. So it says basically make a guess, like look at the picture and make a guess, then algebraically determine whether the graph is symmetric with respect to the y-axis or with respect to the origin. Basically what they want you to do is plug in the negative x value and see what you get out, right? So here, if I were to do this algebraically, let's see what happens if I plug a negative x in. Do I get the exact same thing out? So if you simplify this, negative x squared is actually just x squared minus 5. Yes, I get the exact same thing out. So this is going to be an even function. Okay, and then for this one, I'm going to plug a negative x in. So we want to see if I plug a negative x in, do I get the negative value out that I would have had here? So negative x cubed minus 1. Notice here, this becomes, it just becomes negative x cubed, so that did change negative, but this sign, negative 1, stayed the same, right? This sign did not change. Okay, so it's very important that the whole function would have to change signs for this to work. Okay, so for part B, it appears there's no symmetry, so we conclude after doing the algebra check that this is neither even nor odd. And notice that's what they're doing here. They're plugging in the negative x value, and when they plug it in, they get this guy, right? So therefore, this is not an example of an odd function. You'd have to get the opposite sign on both. Objective 3 says to use a graph to determine whether where a function is increasing, decreasing, or constant. Okay, so you guys, for this, all they're asking you to do is look at the picture and tell where the graph is going down, where it is going up, where it is staying constant. Okay, so let me just see if they're using, you can use interval notation like I taught you. I don't know what your program's gonna make you do. I don't know if they make you choose one or the other. But notice for this, you guys, it's asking where do things decrease? Okay, so I know that from this point here to this point here, the graph is decreasing, right? So for the solution, we're looking at the values of x for which it is increasing, decreasing. Okay, so well, let's look at decreasing first since I talked about that. So decreasing, so it's decreasing. If you want to use your interval notation, it's decreasing from the x value of -6 to -4, right? So that's your interval notation. The other way that you could have said that was between -6, the x value is between -6 and -4. This is where it is decreasing. Then you have to look to make sure there's no other places where it's decreasing. So from here, it's going up, and then it goes constant, and then it goes back down. So from here to here, it's also decreasing, so we have to include that. So that would be from the values 3 to 6. Okay, so from the x values of 3 to 6, it's also decreasing. Yeah, sorry it's not more clear on whether or not they're going to make you do one versus the other, but that's okay. So then for increasing would happen from the x values of -4 to 0. Okay, notice, maybe I'll switch colors here. From -4 up through 0, we are increasing in value. And that's the only place where we're increasing, so that's done. Then it's constant from 0 to 3. So from 0 to 3, it is constant. All right, so that is what they're looking for when they're looking at increasing, decreasing, constant. Where is the graph going down? Where is it going up? Where is it staying the same? Oh, and then they have some actual definitions for these. I wouldn't worry about these definitions. You guys know them, I think. From left to right, is it going up or down, right? Or is it just staying the same? So increasing is going up from left to right. Decreasing is going down from left to right. As you read the graph from left to right, constant just remains the same from left to right. All right, let's look at one more objective for this video, and then we'll break this up into 2 parts here. So objective 4 says use a graph to locate local max and local mins. The definition for local max and local mins, basically, you can read through this official definition, you guys, but essentially all you need to remember is if you have a graph, okay, anywhere where you see a peak or a valley on a graph is a local max or a local min. Okay, so if this was the graph, the one that I just drew, we have a peak here, we have a peak here, we have a peak there. Those are local maximums. Then we have valleys. The valleys happen here, here, and here. Those would be local minimums. Okay, so that's essentially all the definition is it's a local, like, mountaintop or valley, if you can think of it like that. Hopefully that simplifies that definition a little bit for you. Okay, so the figure shows the graph of a function f. It says for part A, at what values of x, if any, does f have a local maximum? List the local maximum values. So notice they're looking for x values. That's very important when you're doing your homework. Okay, so if I were doing this, I would be looking for, since it's a maximum, we're looking for a mountain peak. That only happens right here. The x value there is 0. So I would just say x equals 0. Okay, then for part B, it says at what values of x, if any, does it have a local minimum? Well, my minimums happen here and here. They're the 2 valleys, right? So they happen at x equals -2 and at x equals 1. And then it says find the intervals on which f is increasing, find the intervals on which f is decreasing. Okay, so from left to right, where is this graph going up? It's going up from -2, notice I'm just using the x values, to 0. And then it's also going up from 1 to infinity, right? And we don't ever put brackets on the infinity sign. So that is where it is increasing. It is decreasing from negative infinity, okay, from this direction over here, just coming from negative infinity, all the way to -2, and then it's going down from 0 to 1. So 0, 1. Okay, and that is showing the intervals on which the function is increasing and decreasing. Hopefully that makes sense. And here you have it. So you notice how with the infinity sign, we never use a bracket. Okay, so just be very careful of that. Anyway, that's part C. I think I'm going to stop the video here. We have a couple more objectives to get to. We'll do those next time.